next, let's see, the 27th. So 27th is, I think, a Wednesday. So next Wednesday, we will have a test on all of quarter 4 stuff. So all the energy and chemistry, that will be our test for quarter 4, okay? So you can, right now you can go in and work on, or not today, but like this is available right now, the Unit 4 practice test. So to study for this test, if you have some extra time and you're looking for what to do, this practice test is there. This is pulling from the same test bank as the actual test. So that will help you be familiar with what will be on the test. And also the Bell quiz questions. Those are also from the same test bank. So if you can do the Bell quiz questions, if you can do the Unit 4 practice test, then you'll be pretty prepared for the test. So next time you come on Monday, we'll have a review day. And then when we come on Wednesday, next Wednesday, we'll have our Unit 4 test, okay? And then after that Unit 4 test, we're gonna do a project about energy, and that's the last thing that will go on our grade, okay? So we're getting really close to the end. Also, midterm grades will be posted next Tuesday. So make sure you're thinking about what grades you want posted for midterm grades, okay? I don't know how important those are to you. All right, let's go ahead and today we're going to talk about nuclear energy and energy transformations in nuclear energy, and we're going to review half-life also. So this is our slides. Okay, so most of this should be a review. So look after these questions, think for a minute. So if you can answer these questions, then we won't watch this video. I think we'll be okay without it. So this is from quarter 1. Do you guys remember there's 2 types of nuclear reactions that we talked about? We both start with that. Matthew?
Fusion and fission.
Good, fusion and fission. So the next question up here is, which one is used to produce electricity? Yeah.
Fission.
Good, fission. Fission helps us get electricity. And what one happens in the sun?
Fusion.
Good, the other one, fusion. Perfect. So fission is what happens in nuclear power plants, and fission is what happens in the sun. Right now, there are experiments going that are trying to make fusion happen to get energy out, but they take so much energy to contain the reaction that we don't get any energy out. So in order for fusion to work as a power source, we have to get more energy out than we put in. So that might be sometime in the future we might be able to use fission to produce electricity too. Just not right now. And then, does anyone know this question? I don't think this is one we talked about before. How much more energy does nuclear reaction provide compared to a chemical reaction? Like think of per mass.
10 times more.
It's even higher than that. It's 100,000 times more. If you have gram per gram, nuclear energy is 100,000 times more energy than a chemical reaction. So that has a lot of energy. Okay. And it's windy and our vents are blowing, so that's right. Okay. And then these are 2 other things that we need to remember before we take our test. What is nuclear decay? Can you guys remember? That was quarter 1 as well. Do you remember what we talked about?
Time.
Yep, so that's our half-life. Good. The time it takes for half of the sample to decompose. That's half-life. So nuclear decay is when we have an isotope and it splits. Good. So we talked about alpha, beta, gamma, nuclear decay. So we don't need to know the specifics of nuclear decay. We just have to remember we start with our parent isotope, and then it's unstable, so it undergoes radioactive decay, and the time it takes for half of the sample to decay is our half-life. Do those sound familiar to us from quarter 1? Okay. All right, and then we have this equation. We can use this equation. We're going to talk about how to just reason through some of these. But if we wanted to use the equation, we could figure out the isotope remaining. The isotope remaining is the original mass of our isotope times half to the t. And this t is the number of half-lives that have occurred. So basically, we're just taking our original mass, and however many half-lives we have, we're dividing by 2. So if I have 3 half-lives, then I'm going to divide my original mass by 2 3 times if 3 half-lives have occurred. Okay, so we're going to look at some examples. So here's our first example. Carbon-14 is an isotope of carbon. We use it to carbon date samples. And it has a half-life of 5,730 years. How many grams of a 50-gram sample of carbon-14 is left after 11,460 years? So I like to do these problems using a table. So I need to know the time. I need to know how many half-lives have occurred. And I also need to know how much sample I have, so how many grams. So then we're going to start at time 0. So at time 0, how many half-lives have happened? Also 0, good. And how much sample do I have at time 0?
50 grams.
Good, 50 grams, good. So we start with 50 grams. So whatever, that's called our initial mass. All right, so after one half-life is 5,700 and, is it 30? 30, this is in years. That's one half-life. How much sample do we have after one half-life?
25 grams.
Good, and how did you get that?
Divided by 1/2.
Good, so divide by 2, multiply by 1/2. So we would have 25 grams left after one half-life. And that's this much time. Okay, what about 2 half-lives? So this times 2, or this plus this, that gives us this other number, 11,460. That's 2 half-lives, that many years. How much of our initial isotope mass is left? Good, 12.5. So I just take this amount, I cut it in half because that many years have occurred. And now this would be our answer. How much is left after this many years? 12.5 grams. Questions on that? Does that make sense? Okay. All right. So most of the problems on the test will be graph problems. So let's practice a few of those. If we look at this graph, we should be able to tell how long is our half-life. So looking at this, what do you guys think? How long is the half-life? Sorry?
2.5 years.
Good, yeah. So if you start at 100, half of 100, it's about 2.5 years. Good, perfect. Does that make sense? So the half-life for this isotope, californium-252, we look at where there's half, and it's about 2.5. Okay. All right, let's use another question for this graph. How much would be left after 3 half-lives? Good. Yep, so after 1 half-life, we're at 50%. After 2 half-lives, we're at half of 50, which is 25. After 3 half-lives, we're at 12.5, which is half of 25. Okay. The other way you could do that is you could say 1 half-life is 2.5, 2 half-lives is about 5, 3 half-lives is about 7.5, which gives us about 12.5 again. So the answers for this kind of question on the test will be multiple choice. So you should be able, there should be a big enough gap that you'll be able to pick out the right answer. All right, these are some interesting elements that are used in medicine. So if anyone is interested in medicine, this radioactive decay also has applications in medicine. So for example, if you're going to get a CT scan and they are going to give you some radioactive isotope to see inside of your body, they need to do their scan within the time that there's still radioactive stuff inside of you. So they would have to figure out what is the half-life, how long do we have before we don't have enough to see, to image, okay? So that's kind of interesting. All right, let's go through one more with iodine 131. If we start with 100 grams, how much will be left after 10 days? It's a little bit small.
Like 40 something.
Okay, about 40 something. Okay, good. So we just go after 10 days, that's 10 days. We're about at 40. Good. Somewhere in there. How much will be left after 50 days?
1.2.
Okay, a really small number, right? Yeah. Very good. So 50 will be in here somewhere, and it's going to be between 1.56 and 1.78. And let's talk about this. We talked about this in quarter one, but let's just remember. So this is showing the iodine 131 isotope is decreasing. Is that mass going away? What's happening?
It's turning into something different.
Perfect, good. So along with this graph, we would have our daughter isotope growing in. So iodine 131, iodine 131 isn't there, but just like Isaac said, it's changing into something else. Okay, good. All right, questions on that? Okay, so now we're going to switch gears a little bit, and we're going to talk about nuclear power. So we're going to look at a nuclear power plant, and we're going to try to look and see where there's energy transfers in our building. So first, just take like 5 minutes, read through this sheet. Notice if there's anything interesting that you see, or anything that, just anything that you think is interesting. So this sheet is written in kind of generic terms, and we're going to go in and we're going to fill in some more vocabulary terms. that's been 5 minutes. Are you guys, do you need a little bit more time to read through, or are you ready? Ready? Okay. I can't tell you guys are quiet. Okay, so we're gonna watch this video. As we watch this video, see if you can match these words to our generic words. So if you look at our sheet, there's different, the power building, hot metal side, power side, cooling building, power machine, turning machine. So some of these are going to be matched with some vocabulary words like turbine, generator, light water reactor, uranium-235. So as we go through this video, see if you can list it, see if you can match any of these vocabulary words onto this picture. Does that make sense? Okay. All right, we're gonna watch this video. Oh, it keeps trying to take me back to the...
And we found it frustrating and confusing, so let's try and get to grips with this topic. It all started in the 1940s. After the shock and horror of the war and the use of the atomic bomb, nuclear energy promised to be a peaceful spin-off of the new technology, helping the world get back on its feet. Everyone's imagination was running wild. Would electricity become free? Could nuclear power help settle the Antarctic? Would there be nuclear-powered cars, planes, or houses? It seemed that this was just a few years of hard work away. One thing was certain, the future was atomic. Just a few years later, there was a sort of atomic age hangover. As it turned out, nuclear power was very complicated and very expensive. Turning physics into engineering was easy on paper, but hard in real life. Also, private companies thought that nuclear power was much too risky as an investment. Most of them would much rather stick with gas, coal, and oil. But there were many people who didn't just want to abandon the promise of the atomic age, an exciting new technology, the prospect of enormously cheap electricity, the prospect of being independent of oil and gas imports, and in some cases, a secret desire to possess atomic weapons provided a strong motivation to keep going. Nuclear power's finest hour finally came in the early 1970s, when war in the Middle East caused oil prices to skyrocket worldwide. Now, commercial interest and investment picked up at a dazzling pace. More than half of all the nuclear reactors in the world were built between 1970 and 1985. But which type of reactor to build, given how many different types there were to choose from? A surprising underdog candidate won the day, the light water reactor. It wasn't very innovative, and it wasn't too popular with scientists, but it had some decisive advantages. It was there, it worked, and it wasn't terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. The light water reactor became prevalent because it's simple and cheap. However, it's neither the safest, most efficient, nor technically elegant nuclear reactor. The renewed nuclear hype lasted barely a decade though. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. While in the 1980s, 218 new nuclear power reactors went live, their number and nuclear's global share of electricity production has stagnated since the end of the 80s. So what's the situation today? Today, nuclear energy meets around 10% of the world's energy demand. There are about 439 nuclear reactors in 31 countries. About 70 new reactors are under construction in 2015, most of them in countries which are growing quickly. All in all, 160 new reactors are planned worldwide. Most nuclear reactors were built more than 25 years ago with pretty old technology. More than 80% are various types of light water reactor. Today, many countries are faced with a choice: the expensive replacement of the aging reactors, possibly with more efficient but less tested models, or a move away from nuclear power towards newer or older technology with different cost and environmental impacts. So, should we use nuclear energy? The pro and contra arguments will be presented here next week.
Okay. So go ahead and take a minute and see if you can fill in these vocabulary words. See where you think those should go. If you can talk to your neighbors too. Okay, I'll give you another couple minutes to see if you can match some of those. And we'll see what we think. We'll talk about what we think. Okay. I'm gonna write these on the board so we can see them, and then I'm gonna switch to our document. So we've got the turbine, generator, light, water, reactor, uranium-235, the core. Remember this number? Do you guys remember? This is called our mass number. This is our protons and our neutrons. Core, radiation, and the reactor vessel. So we're going to try to match these. There we go. All right, so did anyone match any of these words on their worksheet? Where do you think that they should go? Oops, that didn't work. Matthew.
Where it says special heat in the paragraph above, it's the second paragraph at the very top. Where it says the special heat, that's radiation.
Okay, special heat, good. Radiation, good. That's the radiation from uranium-235, good. Okay. All right, anything else? Anything else that you matched? Yes, Isaac.
If you go down where it says turning machine and power machine, those are the turbines and generator.
Good, good. So turning machine, that would be our turbine. And this power machine, that's the generator. Good. Good. Okay, so we've got these ones. We've got generator, turbine, and radiation. Good. Julia.
If you go on the bottom left, it says whole in wall metal, that's uranium.
Okay, good. This metal. Anytime it's talking about the metal. Good. That's the uranium-235. Good.
Then where it says like hot metal and hot water,
Uh-huh.
black spot, I said color. That,
Oh, yes. Yep. This thing
yeah.
is the core. Good. So these things are in the core. Good. Okay. So we've got core and uranium-235. So we've got 2 left. Yeah, Matthew.
The core is also the light water reactor.
Good. So yeah, so I might say this whole power building is our light water reactor. That's the type of nuclear power plant. So this is our light water reactor. This whole power building is called this light water reactor. Good. Okay. And then the reactor vessel. So I guess this we have our core in here, and then this thing is the reactor vessel. I don't know how you want to show that. This is our reactor vessel. Okay. All right, questions on that? We got them labeled? Okay, very good. Okay, the next thing that I want you to do is look at your diagram. Let's see if I can just minimize that. And do these next steps. So the first thing I want you to do is circle where energy transfers occur. So an energy transfer, remember, is when energy starts as one form and it transfers to another form. So you should have 3 different places where energy transfers are happening in this power building. So work on that. Once you're done with energy transfers, put a rectangle around things where you think that things could go wrong. So if something could go wrong, put a rectangle. And then go ahead and star parts of the power plant that are to help keep things safe. Or like some kind of safety feature. So I'll give you a few minutes for that. I forgot to mention this. So where the energy transfers occur, go ahead and tell me what energy transfer is happening. So maybe thermal to kinetic or thermal to, I don't know. Tell me what energy transfers are happening. All right, let's go over at least the energy transfers. Let's go back to our ether. So I think that there's an energy transfer happening here where our uranium 235 is heating up the water. So what kind of energy transfer would be occurring? What would we call that? What type of energy starts and where do we end? What type of energy do we end up with?
Radioactive to thermal.
Good, radioactive to thermal. We could also say nuclear to thermal. But let's write that, radioactive to thermal. Good. Okay, where else? I can think of two other places for sure that there's an energy transfer. Matthew.
The turbines, it's
Okay.
heat to kinetic. I mean, thermal to kinetic.
Good, okay.
And then at
We
the
can say
generator, it's
heat
kinetic
to
to electric.
Kinetic. Good. I don't know why I put kinetics. Okay, heat to kinetic and good, then kinetic to, what did you say?
To electric.
Good, electric, good. Good. So there would be one here and then one here. Okay, good. So there are gonna be test questions on this. I think they're pretty straightforward, I just wanted to make sure that you're familiar with those. Does that make sense? You're okay with that? Okay. All right, let's talk about, where do you think things could go wrong? There could probably be a lot of places that things could go wrong, but where did you say there could be something that went wrong?
In the reactor.
Okay, in the reactor, yeah, so in this room somewhere. Lots of things could go wrong. Okay, anything else?
We also turbines.
Yep, so if something happened in the turbine, right, basically anywhere, we could have something go wrong. Maybe like we suck in a fish or something, I don't know. Okay, so there's lots of different places that things could go wrong. How about, are there any places that are there to help us stop a problem or to help us keep things safe?
Control room.
Okay, control room. Hopefully we can monitor what's going on. Yeah, Isaac.
Like emergency room below the core, so if the uranium gets too hot and melts, it goes in there instead of
Good.
everywhere.
Perfect, good. They have built this just in case. But if this gets really hot, they have a backup plan. It'll just spread out on the floor and cool off. Yeah, good. Okay, anything else that you can see? Okay, what about this big dome? So this little building, we usually see this big building. When we see a nuclear, have you guys ever seen a nuclear power plant? Maybe just in a movie. I've seen one in a movie or on TV. Okay, we usually think of this. This is just the cooling building, so this doesn't really have any radioactivity. But if we look over here, this is the reactor building. This building has some thick cement walls, so that could help us keep any radioactivity inside. Okay, so I'm sure there for these last couple, there's lots of different answers. So as long as you have something there, I'm okay with that. All right, this is your assignment for today. So at some point today, make sure you get that submitted. Before, let's see, this is the wrong one. Where were we? Here we go. While you're submitting to Canvas, let's do this. So can you tell me, what is something interesting you learned today? Do you already know all this? Is there anything that stuck out?
That the metal can get so hot it can like turn into the consistency of water.
Yeah, that is pretty interesting. Thank you. Thanks for sharing that. Okay, anyone else? Do you learn anything?
I didn't really get how by just being next to each other. I thought there was a more like a harder process to get them, like get a pump energy into the metals to get it to be like that, but you just put them next to each other.
Okay. Yeah, thank you. That is interesting. Okay, anything else? Okay. Well, hopefully you learned something today. There will be questions, especially about energy transfers in a nuclear power plant on the test. So go ahead and make sure you submit this. And then we have about half an hour of class left. So I would probably, if you're all caught up in all of your classes, I would probably work on the practice test. If you're not caught up in your classes, especially this class, go ahead and look at Canvas, see if there's anything you're missing. If you need help with something, or if you need a paper copy of something, I can get that to you. Keep in mind, next Tuesday is midterms, okay? And midterms during fourth quarter after that it goes really fast. So make sure your grades are where you want them, so that the time goes really fast after that. Okay. All right. So take some time. During this time, I will try to grade stuff. So as you're submitting stuff, I will work on grading. Yes. So you can either pull over desk or sit in that chair. However.